Deep beneath a modern research complex, far below the ordinary noise of roads and cities, machines wait for events that no human eye could ever see. Beams of particles race through tunnels, guided by magnets, measured by instruments built with extraordinary patience. When collisions finally occur, they vanish almost as soon as they appear, leaving behind trails of data that must be reconstructed from fragments. To the people studying them, reality is not presented as a clear picture. It arrives as a pattern hidden inside millions of signals. Now imagine another room, separated not only by distance, but by centuries of thought. There are no superconducting magnets here, no electronic sensors, no walls of computers. Instead, there is a scholar working through compact rules, arranging numbers, testing relationships, and searching for ways to make a difficult calculation suddenly become simple. A problem that appears long may collapse when viewed from a different angle. A complicated surface may hide an orderly structure beneath it. At first, these two worlds seem too different to place in the same story. One belongs to modern particle physics, shaped by laboratories, experiments, and mathematics refined through generations of scientific debate. The other belongs to a much older human fascination with number, pattern, and compressed rules. Yet the title of this story places them side by side and asks a dangerous question. Is modern physics somehow confirming an ancient mathematical vision? Or is the resemblance only visible because modern people are looking backward with knowledge that did not exist before? The most tempting answer is also the easiest. It says that ancient thinkers already knew what modern scientists are only beginning to rediscover. It says that beneath sacred language and short formulas lies a hidden science of particles, fields, and invisible forces. Such an idea has everything a mystery-loving mind could want. It challenges the arrogance of the present. It suggests a forgotten inheritance. It turns history into a locked room and mathematics into the key. But mysteries become more interesting when they survive careful examination. Ancient mathematical traditions developed under very different conditions. Their purposes could include measurement, construction, astronomy, calculation, teaching, or ritual. Their concepts must be understood in the worlds that produced them. To take an old rule and immediately rename it with the language of quantum theory may create excitement, but it can also erase the real achievement hidden in the original context. So the investigation must begin without deciding the answer in advance, with careful patience. The phrase quantum monasticism offers a useful image, but only if it is treated as a metaphor rather than a lost historical school. A monk withdraws from distraction to examine the mind. A theoretical physicist may spend years working through structures that cannot be pictured directly. A mathematician can sit alone with symbols, refusing to accept an answer until every step holds together. Their methods are not the same, and their conclusions are not interchangeable. Yet each represents a form of disciplined attention directed towards something beneath ordinary appearances. That shared discipline may be more important than any claim of secret transmission. Consider what modern physics has gradually learned about matter. The deeper scientists have looked, the less the world resembles the objects of daily life. At human scale, a table seems solid, a stone appears continuous. A flame looks like a single moving thing, but the theories used to describe the smallest known scales rely on structures that are difficult to translate into ordinary images. Fields, probabilities, interactions, and symmetries often matter more than the comfortable picture of tiny solid balls moving through empty space. And still, mathematics works. That is the strange fact at the center of this story. Human beings create symbols on paper, arrange them according to rules, and discover that those symbols can predict events occurring in realms no human sense can directly enter. An equation can point toward the result of an experiment before the experiment is performed. A pattern can reveal what kinds of interactions are possible. A symmetry can restrict what nature is allowed to do. From a distance, this can look almost mystical. Yet the mystery is not that physics has escaped reason. The mystery is that reason reaches so far. Perhaps this is why people are drawn to ancient comparisons. If mathematics can reveal hidden order today, perhaps an older civilization saw the same order first. If modern physicists speak of invisible structures, perhaps ancient philosophers were describing them in another vocabulary. If a short mathematical rule can simplify a complex calculation, perhaps compact Sanskrit expressions contain more than later generations realized. Each of those possibilities feels plausible for a moment. None can be accepted simply because it feels meaningful. A historical connection requires historical evidence. A mathematical equivalence requires mathematics. A scientific validation requires a prediction that survives testing. Without those steps, the connection may still be beautiful, but it remains an analogy, and analogy is not worthless. Sometimes a comparison helps the mind approach an unfamiliar idea. Sometimes two traditions ask similar questions, even when they reach them by different routes. Sometimes the same human desire appears in places that never touched each other. The desire to find unity beneath complexity, order beneath confusion, and a rule beneath the endless variation of experience. That may be the deeper thread connecting the laboratory and the quiet room. One searches for the structure of matter. The other searches for structure in number. Both begin with complexity. Both hope that the correct pattern will make something hidden become clear. Yet before this resemblance can be taken any farther, one phrase must be placed under a brighter light. Vedic mathematics sounds ancient by definition. The name seems to settle its age before the evidence is examined. But names can carry histories of their own, and this one leads to a surprise that changes the entire investigation. Before asking whether quantum physics validates Vedic mathematics, the story must first ask a simpler question. What exactly is Vedic mathematics? The phrase Vedic mathematics has a powerful sound. It suggests age, authority, and continuity. To many listeners, the name alone creates an image of formulas carried intact from a distant sacred past, preserved through generations, and only recently recognized for their scientific importance. Once that image takes hold, every clever calculation can begin to look like evidence of something larger. But history rarely arrives in such a clean package. The system commonly known today as Vedic mathematics is closely associated with Bharati Krishna Tirtha, an Indian scholar and religious leader whose work was published after his death in 1965. The book presents 16 sutras, or concise formulas, along with methods for handling different kinds of arithmetic and algebraic problems. These techniques became popular because some of them are fast, memorable, and satisfying to use. A long multiplication can shrink into a few steps. A difficult-looking expression can become manageable when the numbers are reorganized in the right way. For many people, that efficiency feels like confirmation of great antiquity. Surely, they think, something so elegant must have come from an ancient source. Yet that is precisely where the historical question begins. The claim that these particular 16 sutras come directly from the ancient Vedas has been disputed. Scholars have not simply accepted the modern system as a transparent survival of a complete mathematical tradition recorded in those early texts. This does not mean that India lacked ancient mathematics. Far from it. Indian mathematical history is long, sophisticated, and deeply important. But the history of ancient Indian mathematics and the history of the modern system called Vedic mathematics are not automatically the same story. That distinction changes everything. Imagine entering an old library where several collections have been placed on the same shelf. One contains ancient ritual geometry. Another contains later developments in arithmetic, algebra, and astronomy. A third contains modern explanations of rapid calculation. If every book is labeled ancient Vedic science, the shelf may appear impressive, but the true history disappears. Dates vanish, authors vanish, different purposes become one blurred tradition. The mystery grows stronger when the books are returned to their proper places. Ancient India produced genuine mathematical ideas that deserve to be studied in their own contexts. Some grew from practical needs. Some were connected with ritual construction. Some developed alongside astronomy. Over centuries, mathematical thought changed, expanded, and became more abstract. These traditions do not need to be turned into a single secret code in order to be remarkable. The modern system called Vedic mathematics can also be examined on its own terms. A method may be clever even if its claimed antiquity is uncertain. A computational shortcut may be useful even if it is not a hidden piece of quantum theory. Separating those questions does not weaken the subject. It prevents one claim from borrowing credibility from another. This is where the title of the documentary begins to divide into smaller pieces. There is ancient Indian mathematics. There are Vedic-era texts and practices. There is the 20th century presentation known as Vedic mathematics. And there is modern particle physics. If any connection exists among them, it must be demonstrated across those boundaries rather than assumed, because several ideas can be placed under the same poetic label. For the late-night imagination, this may feel less dramatic than the story of a lost quantum civilization. But it leads toward a more interesting possibility. Perhaps the ancient-modern connection is not a direct chain of formulas. Perhaps it lies in a style of thought that appears whenever mathematics becomes powerful, the search for patterns, transformations, relationships, and compressed procedures. That possibility is harder to prove and easier to misunderstand, but it avoids the need to pretend that one tradition secretly contained another. There is another reason the distinction matters. When people claim that ancient scholars already knew modern physics, they often believe they are honoring the past. Sometimes they are trying to correct a genuine imbalance. Histories of science have not always given equal attention to achievements outside Europe. Important contributions from India, China, the Islamic world, Africa, and other regions have often been simplified in popular education. But exaggeration can create a new kind of erasure. If every authentic ancient achievement is replaced by the claim that it was secretly quantum mechanics, then the real achievement becomes harder to see. A geometric method is no longer valued for what it actually solved. An astronomical calculation is no longer understood in the world that produced it. Everything is praised only because it can be made to resemble the present. The past deserves more respect than that. To understand whether ancient Indian mathematical traditions offer meaningful parallels with modern physics, the investigation must first recover the older landscape without forcing 21st century language onto it. That means returning to periods when mathematics was not separated neatly into modern school subjects, when geometry could be tied to construction, when astronomical observation could demand precise calculation, and when knowledge was preserved through forms very different from a modern textbook. There, the word ancient becomes more than decoration. It becomes a world of actual problems, actual techniques, and actual intellectual choices. And once that world is visible, a subtler question can be asked. When did mathematics begin to move beyond the objects in front of it? When did a line become more than a line drawn on the ground? When did a number become something that could be transformed according to rules, even when no physical objects were present? Those questions lead farther back than the modern 16 sutras. They lead toward the deeper history of abstraction itself. In other words, the first discovery is not a formula, but a boundary. On one side stands documented history, on the other stands interpretation. The two can speak to each other, but they cannot be quietly exchanged. Keeping that boundary visible will allow the story to travel much farther without turning curiosity into certainty before the evidence has earned it. That is where the next chapter begins. Long before mathematics became a subject separated into classrooms, textbooks, and specialized departments, it lived inside the practical demands of human life. People counted because goods had to be exchanged. They measured because land had boundaries. They watched the sky because seasons returned, ceremonies depended on timing, and journeys could be guided by patterns overhead. They constructed because a building or ritual space could not be made accurately by intention alone. In ancient India, mathematical thinking emerged within this wider world of activity. It was not a modern discipline waiting to be discovered under an older name. It was woven through problems that belonged to its own time. This matters because the modern imagination has a habit of looking backward and renaming the past. A geometric procedure becomes advanced engineering. A pattern in numbers becomes computer code. A philosophical statement about reality becomes quantum mechanics. The older idea is lifted out of its setting and placed inside a modern framework that would have been unfamiliar to the people who created it. The result can sound impressive, but it often tells us more about the present than about the past. To understand ancient mathematics honestly, the first task is therefore an act of patience. The listener must resist the desire to ask whether a procedure resembles something modern, and instead ask what problem the procedure was designed to solve. Consider the traditions connected with the Sulba Sutras, texts associated with rules for constructing ritual altars. Their geometry is important because it reveals disciplined knowledge of measurement, shape, transformation, and spatial relationships. Ropes, lines, lengths, and areas were not merely physical objects. They became part of procedures that could be taught and repeated. The scene is easy to imagine in the quiet of night. A piece of ground must be prepared. Proportions matter. A form must be constructed correctly. A mistake cannot be hidden behind a vague explanation. The builder must know where to place the line, how to compare one length with another, and how to transform one shape while preserving what matters about its area. There is nothing quantum about this, and that is exactly why it is so interesting. The achievement belongs to the long human movement, from direct action toward abstract rule. At first, a relationship is discovered because a practical task demands it. Later, the relationship can be remembered independently of the original task. Eventually, the rule can be studied for its own sake. This is the birth of a strange kind of freedom. Once a pattern is abstracted, it can travel. A method learned while constructing one object can be applied to another. A relationship between lengths can become a general principle. A numerical procedure can survive even when the objects that first required it have disappeared. The mind begins to handle structures that no longer need to remain attached to a single physical example. Modern people are so accustomed to this that the transformation is almost invisible. Children learn numbers before they understand how radical the idea of number really is. The symbol 5 can refer to stones, stars, years, people, or nothing present at all. The objects change, yet the relationship represented by the number remains available. That is a form of intellectual technology. It allows the mind to separate structure from substance, and once that separation is possible, mathematics becomes capable of describing worlds that ordinary experience cannot easily picture. This is where the documentary's larger mystery begins to take shape, but the connection must be handled. Ancient Indian mathematicians were not secretly writing the equations of quantum field theory when they measured ritual spaces. Yet the habit of abstraction that mathematics develops over centuries is one of the same broad human capacities that later makes modern theoretical physics possible. The connection is not a hidden transmission. It is a continuity in what mathematical thought can do. A direct historical claim says that one body of knowledge caused or contained another. That kind of claim requires evidence showing texts, teachers, translations, or lines of influence. A thematic parallel says that similar intellectual moves can appear in different places because people face similar logical problems. That is a weaker claim, but often a more believable one. When a culture learns to reason about proportion, it does not need to know about particles to have crossed an important threshold. When a procedure becomes general enough to survive its original context, something profound has already happened. The mind has discovered that reality can be represented by relationships that are not identical to the objects themselves. This is why the ancient story should not be rushed. The measured ground matters because it teaches the mind to trust a relationship. The repeated procedure matters because it separates knowledge from a single event. The preserved rule matters because it allows one person's discovery to become another person's starting point. Across generations, these habits accumulate. Mathematics becomes less tied to immediate objects and more capable of operating on symbols, forms, and relationships. The world is still present, but the mind has begun to build a second world alongside it, a world of structures that can be explored even when nothing physical is being touched. That second world will eventually become powerful enough to describe things no ancient observer could have measured, and no modern observer can see directly. Ancient Indian mathematics develops through many periods and many purposes. Geometry is only one part of the story. Arithmetic grows in sophistication. Astronomical calculation places new demands on accuracy. Algebraic reasoning appears in forms shaped by particular problems and traditions. Ideas travel, change, and are reworked. And development means that mathematics itself is changing from a collection of useful procedures into something increasingly capable of revealing relationships beyond the immediate task. The next section follows that transformation more closely. It asks what happens when the object begins to disappear and the relationship remains, because that quiet shift will eventually bring ancient mathematical thought and modern physics into their most meaningful point of comparison. A line drawn in dust is temporary. Wind can erase it, feet can cross it, rain can dissolve it until no trace remains. Yet the relationship that line represents can survive perfectly in the mind. This is one of mathematics' quiet miracles. A physical example may vanish while the structure discovered through it remains available for centuries. Geometry offers a clear way to see this transformation. A shape may begin as something that must be constructed in a particular place for a particular purpose. The measurements matter because the object must work. But once the relationships among the sides, angles, lengths, and areas are understood, the shape is no longer trapped inside that one construction. It can be imagined. It can be redrawn. It can be transformed. It can be compared with another shape that has never physically existed. The same movement occurs with number. Counting may begin with objects, yet the number itself gradually becomes independent of them. 3 stones and 3 stars share no material substance, but they can share a numerical relation. Once that relation is recognized, mathematics begins to operate in a domain where the material identity of the objects matters less than the structure connecting them. This change is so familiar to modern minds that it can be difficult to feel its strangeness, but it contains the seed of nearly everything that follows. When relationships become more important than things, mathematics gains the ability to cross boundaries. A procedure developed in one setting can appear again in another. A rule about proportion can move from construction to astronomy. A numerical method can become useful in trade, calculation, or theoretical work. The pattern travels because it is no longer owned by the object that first revealed it. Indian mathematical history contains many examples of this growing power of abstraction across long periods. Different scholars and traditions worked on arithmetic, geometry, astronomy, algebraic problems, and methods of calculation. The story was not a single straight line, and it was not isolated from exchange with other cultures. Mathematical knowledge has always moved through encounters, translations, adaptations, and rediscoveries. That complexity is worth preserving. The myth of a single ancient source that already contained everything can seem grand, but it makes intellectual history smaller. Real history is more interesting because ideas change when people use them. Methods are refined, notation improves, questions that once seemed impossible become ordinary, and new questions appear in their place. Over time, mathematics becomes increasingly comfortable with entities that are not ordinary objects. A symbol can stand for an unknown quantity. A relation can be manipulated before the value of that quantity is known. A rule can apply to an entire class of problems rather than one example. The mind learns to reason inside structures. This is where the comparison with modern physics becomes tempting. In the smallest realms described by quantum theory, the old language of solid objects becomes unreliable. Physicists still use words such as particle, but the mathematical framework often matters more than the picture suggested by the word. What can be measured, how systems interact, how probabilities change, and what symmetries constrain the theory become central. The modern world has therefore arrived at an extreme version of an ancient mathematical habit, trusting relationships beyond what the senses can directly represent. To say that both ancient mathematics and modern physics use abstraction is not to say that ancient mathematicians possessed modern physical theories. The distance between those claims is enormous. Abstraction is a general capacity. Quantum field theory is a highly specific scientific framework built through modern mathematics and experiment. The earlier knowledge may be genuine and sophisticated without containing the later theory. Still, the comparison reveals something deeper about the human mind. Why does abstraction work at all? Why can a relationship discovered in one context survive and reappear somewhere completely different? Why can mathematics leave the world of immediate objects, wander through a realm of symbols, and then return with predictions about the physical world? These questions are not answered simply by pointing to history. They are philosophical questions, hiding inside scientific success. A person looks at a triangle, then closes their eyes. The triangle as a physical drawing is gone, yet the mind can still reason about its properties. A physicist studies a mathematical object that cannot be pictured as a normal shape, then uses it to predict what a detector will record. In both cases, the mind has stepped away from appearance and trusted structure. This may be the most meaningful bridge in the entire documentary, precisely because it does not require a secret lineage. It suggests that mathematical thinking repeatedly advances by learning which features of a problem are essential and which are accidental. The color of a drawn triangle does not matter to its geometry. The material of a counted object does not matter to its number. The particular picture used to imagine a quantum process may not matter if the mathematical predictions remain correct. Again and again, knowledge grows by discarding what is unnecessary. That process creates a sense of hidden depth. The visible world appears full of differences, But mathematics finds structures that remain stable beneath them, and once people become accustomed to that idea, a dangerous thought becomes almost irresistible. Perhaps everything is governed by a small set of hidden rules. Modern physics will take that hope farther than ancient mathematics ever could, not because the ancients failed, but because new instruments, new experiments, and new mathematical languages opened questions that earlier generations had no reason to ask. The story now moves toward that rupture. At the beginning of the 20th century, scientists studying light, heat, atoms, and radiation encountered results that refused to fit the comfortable picture of classical physics. Matter stopped behaving like the matter people thought they knew, and in the confusion that followed, mathematics would become not merely a tool for describing reality, but a guide through a reality that the human imagination could no longer see clearly. By the end of the 19th century, many physicists believed the great structure of nature was nearly complete. The world seemed governed by laws that described motion, forces, heat, electricity, magnetism, and light with remarkable success. There were still problems, of course, but the basic picture appeared familiar. Matter was made of things. Those things occupied places. Causes produced effects. If enough information were known, the future could in principle be calculated from the present. Then small cracks began to appear. Experiments involving light, heat, and atoms did not fit comfortably inside the older framework. The details were technical, but the emotional effect was simple. Nature was refusing to behave the way sensible objects were supposed to behave. Light could not be described by one ordinary picture alone. Matter revealed discrete patterns where continuous behavior had been expected. At very small scales, the language that worked so well for planets, projectiles, and machines began to fail. The response was not a single dramatic discovery made in one night. It was a slow revolution, built from problems that would not go away. Physicists proposed new mathematical rules because the experiments demanded them. Those rules worked, yet they often produced a world that was difficult to imagine. Probability entered at a fundamental level. Certain quantities could not be treated as though they possessed simple, simultaneously knowable values in the way classical intuition expected. The act of measurement could no longer be described as a completely passive glance at a tiny object already carrying every familiar property in a familiar way. For the human mind, this was deeply uncomfortable. People are trained by daily life to think in pictures. A ball has a location. A stone has a path. A door is open or closed. A sound comes from somewhere. These categories are useful because the scale of ordinary life rewards them. Quantum theory did not destroy reality. It destroyed the assumption that reality at every scale had to resemble everyday experience. This is the point where mystery enters the popular imagination. Once scientists begin saying that particles do not behave like tiny marbles, that probabilities matter, or that measurement plays a strange role, the language starts to sound philosophical. The listener hears words such as uncertainty, observer, and state, and those words seem to invite connections with older traditions of thought. Perhaps, some suggest, ancient philosophers already understood what modern physics has only rediscovered. The suggestion is emotionally powerful because quantum theory already feels like a challenge to ordinary materialism. If the smallest scales of nature are strange, maybe old metaphysical ideas were scientific after all. If observation matters, maybe consciousness creates reality. If two systems can become entangled, maybe every spiritual teaching about unity has been experimentally confirmed. But the distance between a scientific result and a philosophical interpretation can be larger than it first appears. Quantum mechanics became successful not because its concepts sounded profound, but because its mathematics made predictions that agreed with experiments. The theory could be used to calculate outcomes. Its strange rules were not accepted because they matched an ancient text. They were accepted because nature kept behaving in ways the new framework described better than the old one. A theory that sounds mysterious can still be wrong. A tradition that contains deep philosophy can still be unrelated to a particular physical equation. Similar language may create a bridge in the imagination while leaving the mathematics on opposite shores. And yet, even after every exaggerated comparison is removed, something astonishing remains. The equations work. Human beings evolved to judge distance, recognize faces, avoid danger, and handle objects at ordinary scale. Nothing in daily survival required an intuitive picture of the quantum world. Yet mathematics developed by human minds can describe that hidden realm with extraordinary precision. A physicist can write symbols on a page, follow rules that may have no simple visual equivalent, and predict what a detector will record. This is a deeper mystery than the claim that an ancient verse secretly contained quantum physics. Why should abstract mathematics reach into nature so effectively? The question becomes even stranger when the old image of particles is examined. The word particle suggests a tiny object, something like a grain of sand, made unimaginably small. But modern particle physics does not simply consist of smaller and smaller solid pieces. The theoretical framework describes quantum fields, interactions, states, and symmetries. What people call particles appear within this deeper structure. The comfortable picture begins to dissolve. A field is not an ordinary substance spread through space like mist. A quantum state is not simply a hidden photograph waiting to be uncovered. The mathematics provides rules for what can happen, what can be measured, and how probabilities are related. For many listeners, this is the moment when physics begins to feel less like machinery and more like a code. But even that metaphor can mislead. The sense of mystery comes from the gap between prediction and picture. Scientists can often calculate more confidently than they can visualize. They can know what a theory says will happen without agreeing on a single everyday story about what reality is doing between measurements. That gap has made quantum mechanics fertile ground for philosophy, speculation, and myth. Yet it also teaches a lesson that echoes through the history of mathematics. Sometimes structure is more reliable than image. An ancient geometer could trust a relationship even after the original drawing was erased. A modern physicist can trust an equation even when no simple mental picture captures the process completely. The comparison is not proof of historical transmission. It is something quieter. It is the repeated discovery that the mind can move beyond what the senses present and still return with knowledge that works. The next step takes that discovery further. If particles are not merely tiny objects, what are they within the modern theory? And why do physicists speak so often about symmetries, transformations, and invisible fields when describing the deepest known structure of matter? The popular image of particle physics is crowded with tiny objects. Electrons, quarks, neutrinos, photons, and other names appear like entries in a strange microscopic catalogue. It is easy to imagine the universe as a box filled with particles, each one a smaller version of the solid things seen in daily life. The modern theory is less intuitive than that picture. In quantum field theory, fields are fundamental parts of the description. What people call particles can be understood as excitations associated with those fields. The mathematics is demanding, but the idea needed here is simple. The deepest framework is not merely a list of little objects. It is a system of fields, interactions, and rules. This changes the question a physicist asks. Instead of only wondering what the smallest thing is made of, the physicist may ask how the theory behaves when its description is transformed. What can change without changing the physical content? What relationships must remain consistent? What kinds of interactions are permitted by the mathematical structure? This is where symmetry becomes central. To ordinary eyes, symmetry means visual balance. A butterfly appears similar on both sides. A snowflake repeats a form. A wheel looks nearly unchanged after rotation. Physics uses the idea more broadly. A symmetry can describe a transformation under which the essential form of the laws remains unchanged. The object may be described differently, or a mathematical quantity may be transformed, yet the physical predictions retain a crucial invariance. This sounds abstract because it is abstract, but the consequences are concrete. Symmetry principles help organize the standard model, the modern framework describing known elementary particles and three of the fundamental interactions. They are not decorative features added after the theory is complete. They are woven deeply into how the theory is constructed. For a listener following the mystery of ancient mathematics, this creates an immediate temptation. Here is modern physics saying that hidden structure matters more than surface appearance. Here are mathematical transformations revealing what remains unchanged. Here is complexity organized by a smaller set of rules. Does this not sound like the ancient search for compact formulas and patterns? In a broad sense, yes. In a technical sense, the comparison must be handled with care. A mental multiplication method and a gauge symmetry are not the same mathematical thing. A shortcut for manipulating numbers does not become a theory of particle interactions, because both involve patterns. The distance between them cannot be crossed by metaphor alone, yet the attraction of the comparison reveals something important about human reasoning. People are fascinated by transformations that preserve something hidden. A shape can rotate, while its essential form remains recognizable. A calculation can be rearranged while its answer remains unchanged. A physical theory can be expressed in different mathematical ways, while preserving the predictions that matter. Across these very different cases, the mind learns to ask the same broad question: what is fundamental, and what is merely the way the problem happens to be presented? That question is one of the most powerful in science. A surface feature may be accidental. A coordinate system may be chosen for convenience. A symbol may be replaced by another symbol. A calculation may be reorganized. If the underlying relationship survives, then perhaps the relationship is closer to the heart of the problem than the original appearance. Modern physics pushes this idea into territory that would have been unimaginable to ancient mathematicians, but the intellectual instinct is recognizable. Look beneath the surface. Search for what does not change. Find the structure that remains after unnecessary details are removed. This is the point where the documentary's title becomes both more interesting and less literal. If quantum physics is not validating a set of ancient computational rules, perhaps it is revealing why human beings repeatedly value certain forms of mathematical thinking: compression, symmetry, transformation, invariance, economy. These are not secret messages from one age to another. They are recurring strategies for dealing with complexity. The universe presents an enormous variety of phenomena. Different particles have different properties. Interactions appear in different forms. Experiments produce vast quantities of data. A theory becomes powerful when it finds a smaller structure capable of organizing that variety. The same emotional satisfaction appears when a long calculation suddenly collapses into a short rule. What looked complicated is revealed as an instance of something simpler. This does not prove that the two simplifications share an origin. It explains why the comparison feels so compelling. The human mind loves the moment when many things become one pattern. That love can guide discovery, but it can also mislead. A beautiful unification may fail. A simple story may ignore evidence. A pattern may be real in one domain and merely suggestive in another. So the investigation must keep two truths together. First, modern particle physics genuinely relies on deep mathematical structures, including symmetries that shape the form of the theory. Second, the existence of those structures does not retroactively transform unrelated ancient formulas into quantum physics. Between those truths lies the more subtle mystery. Why does nature allow so much complexity to be organized by symmetry at all? Why can changing a description reveal something that remains unchanged beneath it? Why do physicists often learn more by studying the rules of transformation than by trying to imagine a tiny object directly? This point also changes the emotional shape of the mystery. The question is no longer whether an old rule contains a modern particle name waiting to be decoded. It is whether the success of structural reasoning across very different ages and problems reveals something far more persistent about mathematics itself: its ability to ignore appearances, preserve relationships, and discover order where ordinary intuition sees only separate things. The next chapter follows this question into the idea of symmetry itself. There, the story will leave the visual symmetry of shapes behind and enter a stranger realm where the laws of nature can be constrained by what they are forbidden to change. Symmetry seems simple when it is first noticed. A face has two sides. A wheel can turn and still look the same. A pattern repeats around a center. Children recognize symmetry long before they know the word. But in physics, symmetry becomes something much more powerful than visual balance. The deeper idea is transformation. Suppose a description is changed in a particular way, yet the essential physical law remains unchanged. The appearance may differ, the coordinates may differ, the mathematical expression may be rewritten, but something underneath survives. That survival can be more important than the surface form. This is where the universe begins to look less like a collection of objects and more like a structure governed by permissions and restrictions. A theory does not only say what exists, it also says what transformations can be made without altering the physical content. Those allowed transformations can reveal what is fundamental. In some cases, they can restrict the form of the laws themselves. For the listener, This can be pictured as a locked room with many doors. The furniture may be moved, the lights may change. The room can be described from different corners, yet certain relationships remain fixed. If those relationships survive every permitted rearrangement, perhaps they belong more deeply to the room than the particular view from one doorway. Modern theoretical physics often works in this spirit. The physicist does not always begin with a clear image of a tiny object and then write an equation that describes it. Sometimes the mathematical structure comes first. Consistency, symmetry, and transformation narrow the possibilities. The theory becomes a map of what nature is allowed to do before every detail has been seen directly. This is one reason modern physics can feel almost forbidden to an outsider. It suggests that reality may obey a hidden grammar. The grammar is not hidden because someone deliberately concealed it. It is hidden because human senses were never designed to perceive it directly. People see objects, colors, movement, and distance. They do not see gauge symmetries floating in the air. They do not experience conservation laws as visible walls. Those structures are inferred through mathematics and experiment, and yet they have consequences. A symmetry can be related to a conserved quantity. A requirement of consistency can exclude certain possibilities. A mathematical transformation can show that two apparently different descriptions are really expressions of the same physical situation. The effect on the imagination is profound. What if the deepest truths are not things at all? What if they are relationships that survive change? This is where the comparison with ancient mathematical thought becomes tempting again. Older traditions also learned that a relationship could remain stable while the objects carrying it changed. A ratio could appear in different settings. A geometric relation could survive a redrawing. A numerical pattern could be recognized across many examples. But the same warning returns. A general resemblance in method does not establish a direct historical connection. Ancient mathematicians who studied proportion were not secretly deriving the symmetries of the standard model. The mathematical objects are different. The scientific questions are different. The tools are different. Still, there is a meaningful human continuity. Whenever mathematics becomes more abstract, it becomes more interested in what remains invariant beneath transformation. This idea appears in different forms across many areas of thought. Change the position, but preserve the distance. Change the notation, but preserve the equation's meaning. Change the coordinates, but preserve the physical prediction. Rearrange the calculation, but preserve the answer. The mind begins to suspect that invariance is a clue. Something that survives many transformations may be closer to the structure of the problem than the particular form in which it first appeared. That suspicion is powerful enough to guide discovery. And it also explains why symmetry attracts mystical language. A hidden order beneath change sounds philosophical. An invisible rule that governs many appearances sounds ancient. A unity behind variety sounds spiritual. But physics does not stop at the poetry. The symmetry must be defined mathematically. Its consequences must fit the rest of the theory. The theory must survive experiment. Without those steps, symmetry becomes only a metaphor. With them, it becomes a tool. The distinction is the same one that has followed the documentary from the beginning. Wonder can open the door, but evidence decides how far the story may travel. This does not make the story less mysterious. In fact, the real mystery may be stronger. Why should nature possess symmetries that mathematics can uncover? Why should transformations that exist first as abstract possibilities in the mind correspond to measurable features of the physical world? Why can the universe be constrained by rules that human beings discover through symbols? No ancient text is required for those questions to feel profound. They arise directly from the success of physics itself, and they lead toward the next comparison. The modern Vedic mathematics tradition is admired partly because it offers short procedures that can make long calculations easier. The appeal is immediate. Complexity gives way to a compact rule. Symmetry in physics can also make complexity more manageable, though in a completely different mathematical way. So the question becomes more precise. Is the attraction between these two worlds really about shared formulas? Or is it about a deeper human fascination with compression? The belief that a long and confusing surface may be generated by something much smaller underneath. There is also a quieter lesson hidden inside symmetry. A change can be dramatic without being fundamental. A description can look completely different while preserving the same underlying content. This teaches the listener to distrust appearances in a disciplined way. Not every difference matters equally. Sometimes the most important fact is precisely what refuses to change, even while everything visible around it seems to move. That is why invariance feels almost like discovery. The next section enters that possibility, where the shortest rule can feel like a secret, even when no secret history exists at all. There is a particular kind of pleasure in watching a long calculation collapse. At first, the page is crowded. Numbers stretch across lines. The obvious method appears slow. Then someone notices a pattern. A pair of values can be reorganized. A complement can be used. A repeated operation can be replaced by a shorter rule. Suddenly, the problem looks smaller. This pleasure helps explain the enduring popularity of methods taught under the name Vedic mathematics. Some techniques are presented as ways to recognize numerical structures quickly and perform calculations with less written work. For students and mental calculators, the experience can feel almost magical. But what feels like magic is often a change of representation. The problem itself has not been broken. The answer has not been guessed. The same numerical relationship is being approached through a different route. This is an important distinction because it points toward a broader mathematical habit. Many difficult problems become easier when they are expressed in a better form. A complicated fraction may simplify after cancellation. A geometric problem may become clearer when redrawn. An equation may reveal its structure after substitution. A physical theory may become easier to understand when a symmetry is recognized. The details differ, but the emotional effect is similar. What looked like complexity turns out to contain redundancy. The mind had been carrying information that was not necessary. Once the unnecessary part is removed, the hidden structure appears. This is where popular comparisons can become dangerous. Because both a computational shortcut and a physical symmetry can reduce complexity, it is tempting to say they are the same kind of knowledge. From there, it is only a small rhetorical step to claim that the ancient rule already contained the modern physics. But similarity of effect does not mean identity of mathematics. A shortcut for multiplying certain numbers is not a gauge principle. A compact arithmetic procedure does not describe quantum fields. The word pattern is too broad to carry that conclusion by itself. Still, the comparison has uncovered something worth keeping. Human beings are fascinated by compression. A short story that explains many events feels powerful. A law that unites several observations feels deeper than a list of separate facts. A formula that replaces pages of calculation feels elegant. A theory that describes many particles through a smaller set of principles feels closer to the architecture of nature. The dream is always the same. Find the smallest rule that explains the largest amount. This dream appears in mathematics, science, philosophy, and even religion. It appears whenever people search for unity beneath variety. That does not mean all forms of unity are equivalent. It means the human mind repeatedly values explanations that compress. Perhaps this is the real reason a modern listener can hear a Vedic sutra and think of theoretical physics. The connection may not lie in the specific content. It may lie in the form of the promise. A sutra is short, an equation is short. The world they seem to organize is large. The contrast creates a feeling of depth. If a few symbols can govern many cases, then perhaps the symbols have reached something fundamental. But simplicity can deceive. Not every short rule is deep. Not every elegant theory is true. A method may work only in a narrow range of problems. A beautiful physical model may fail when tested against observation. Nature is not required to reward human taste. This is another point where modern physics differs from mystical interpretation. Physicists may admire an elegant theory, but admiration cannot substitute for evidence. The theory must match measurements. If nature disagrees, the beauty of the mathematics cannot rescue it. The same discipline should guide historical claims. A compact rule may be old or new. Its age must be established historically. A method may resemble another method. The relationship must be demonstrated mathematically. A philosophical idea may sound modern. Its meaning must be understood in its original context. Otherwise, compression becomes a story about compression, rather than evidence of connection. Yet the hunger for simple order remains. Seen this way, the fascination with short rules is not childish or naive. It reflects one of the deepest ambitions in intellectual history. People want to know whether the apparent clutter of the world can be reduced without being distorted. They want to discover whether complexity is essential or merely the result of viewing a simpler structure from the wrong angle. Mathematics repeatedly rewards that hope, but never promises that every mystery will yield. The strongest explanation is therefore not always the shortest one, but the shortest one that keeps every important fact and survives every serious test repeatedly. This hunger becomes especially powerful when the subject turns to zero. Few symbols appear simpler. A small mark can represent the absence of a quantity, hold a place inside a numeral, participate in calculation, and transform the structure of mathematical notation. To the imagination, zero also opens a door into philosophy. It seems to point toward emptiness, nothingness, the void, and the possibility that absence itself can have meaning. Then modern quantum theory enters the conversation with the idea of a vacuum that is not simply an empty box. The temptation is immediate. Ancient ideas of emptiness, mathematical zero, and the quantum vacuum are placed side by side, and the resemblance begins to look like proof. But the word nothing is one of the most dangerous words in the entire story. It sounds precise because it is short. In reality, it changes meaning depending on the system in which it is used. Mathematical zero is not automatically philosophical emptiness. Philosophical emptiness is not automatically a quantum vacuum. A quantum vacuum is not ordinary nothingness. The similarities are real at the level of language and intuition, but the differences are just as important. The next chapter follows that confusion into the apparent emptiness of zero, where the documentary will ask whether nothing can truly be the same thing in mathematics, philosophy, and physics. Nothing seems easier to understand than nothing. An empty hand contains nothing. An empty chair holds no one. A blank space appears to contain no object at all. Yet the moment the word enters mathematics, philosophy, and physics, it begins to split into different meanings. Mathematical zero is not ordinary emptiness. It is a formal part of a system. It can mark the absence of a quantity. It can hold a position inside a numeral. It can be added, subtracted, multiplied, compared, and used inside equations. Its role depends on mathematical rules. Philosophical emptiness is something else. Different traditions use ideas of emptiness, void, absence, or non-being in different ways. Some concern the nature of identity, some concern impermanence, some concern the limits of language, or the way the mind constructs distinctions. These ideas can be profound without being numerical. Then there is the quantum vacuum. To a casual listener, vacuum sounds like nothing. But in modern quantum field theory, a vacuum state is not simply the absence of everything in the everyday sense. It belongs to a mathematical and physical framework in which fields remain part of the description. Now the temptation becomes obvious. Mathematics has zero. Ancient philosophy speaks of emptiness. Quantum physics has a vacuum. Place the three ideas beside each other, and they begin to look like different names for the same hidden truth. But the resemblance is created partly by language. The same word can point toward different structures. A person may say an account has zero money, a room is empty, and a vacuum contains no particles in a particular state. Those statements can all involve absence, yet the kind of absence is not identical. This is why comparison requires definitions. Without them, the mind fills the gaps. It hears a familiar word and assumes a familiar meaning. Then it carries that meaning into a new subject, where the rules are different. The result can be a beautiful mistake. For example, a philosophical teaching about emptiness may be interpreted as though it were making a claim about quantum fields. But unless the teaching defines the same mathematical objects, makes the same physical predictions, and can be connected to the scientific theory through evidence, the similarity remains philosophical rather than scientific. That does not make the teaching false. It means it is answering a different kind of question. This distinction is easy to lose because modern culture often treats science as the highest form of validation. If an ancient idea can be described as quantum, it seems to gain authority. A spiritual teaching becomes more impressive if it can be linked to physics. A mathematical tradition becomes more advanced if it can be connected to modern technology. But this desire can distort both sides. Ancient philosophy does not need a particle detector to be meaningful. Modern physics does not need spiritual language to be mysterious. Each becomes clearer when allowed to remain itself. The idea of zero offers a perfect example. Zero is powerful because mathematics gives it a precise role. That precision allows calculations to remain consistent. It allows place-value systems to represent numbers efficiently. It allows equations to distinguish between a quantity and its absence. Its power comes from definition. The quantum vacuum also gains meaning from definition. It exists inside a theory with mathematical rules. Physicists can calculate properties associated with it. They can ask how fields behave in a particular state. Again, its power comes from structure. The philosophical void may gain meaning through a completely different route, perhaps by challenging the assumption that things possess fixed independent essence, or by examining how concepts arise. The words may sound similar in translation. The structures are not automatically the same. This becomes one of the most useful lessons in the documentary. When two ideas appear to match, ask whether the match survives definition. Do the terms refer to the same thing? Do the systems use them in the same way? Do they produce the same consequences? If not, the resemblance may still inspire thought, but it cannot carry the full weight of validation. The word nothing, therefore, turns out to be crowded. Inside it are several different forms of absence, each belonging to a different world of meaning. This is more interesting than the easy claim that they are all identical. It suggests that even emptiness depends on context. What counts as nothing in one system may still contain structure in another. An empty box is not the same as zero on a page. Zero on a page is not the same as a vacuum state. A vacuum state is not the same as a philosophical teaching about emptiness. The differences matter, and yet the repeated human fascination with absence is itself worth noticing. Across mathematics, philosophy, and physics, people keep asking what remains when something is removed. Take away objects, take away quantity, take away familiar properties. What is left? The question changes its meaning each time, but the impulse is recognizable. Perhaps this is another reason ancient and modern ideas seem to resonate. They often begin at the edges of ordinary language, where familiar words are stretched toward unfamiliar territory. At those edges, misunderstanding becomes easy. So does discovery. The distinction also protects the atmosphere of mystery from becoming careless. A mystery is strongest when the unknown is defined clearly enough to resist easy answers. If every absence is called the same emptiness, there is nothing left to investigate. But when each meaning is separated, the listener can begin to notice the precise places where mathematics, philosophy, and physics genuinely touch, and where they only appear to overlap in practice. The next section will apply the same caution to other seductive parallels: unity, cycles, uncertainty, opposites, transformation, and interconnectedness. Each can sound like a bridge between ancient thought and quantum physics. The challenge is to discover which bridges are strong enough to cross, and which exist only because the same words have been placed on both sides of the river. Once people begin searching for parallels between ancient thought and quantum physics, the list can grow quickly. Ancient texts speak of unity. Quantum physics speaks of entanglement. Ancient traditions describe cycles. Physics describes oscillations and changing states. Philosophers discuss opposites. Quantum theory contains mathematical alternatives, complementary descriptions, and probabilistic outcomes. The words line up so neatly that the conclusion can feel obvious. But similarity of vocabulary is one of the weakest forms of evidence. A broad word can travel almost anywhere. Unity may mean spiritual oneness, political unity, mathematical identity, physical interaction, or simply the fact that several things belong to one system. The word remains the same, while the structure underneath it changes completely. This is why retrospective interpretation is so powerful. After a modern discovery becomes famous, readers return to older writings and notice phrases that seem to resemble it. The old passage is then read through the lens of the new knowledge. The resemblance feels predictive. But there is a test that can reveal the difference between prediction and reinterpretation. Could the modern scientific meaning have been identified from the ancient statement before the modern discovery was known? If the answer is no, then the old statement may be flexible enough to support many later interpretations. A phrase about hidden unity can be connected to entanglement after entanglement is discovered. It could also be connected to ecology, social cooperation, gravitational systems, or the interconnectedness of trade. The flexibility makes the phrase philosophically rich. It makes it scientifically non-specific. This does not mean that ancient thinkers were vague or confused. It means they were often asking different questions. A philosophical text may explore the nature of self, perception, change, or ultimate reality. A scientific theory must define measurable quantities and relationships. The two forms of inquiry can influence each other, but they do not become equivalent simply because they share a metaphor. The documentary therefore uses three questions whenever an ancient-modern parallel appears. First, are the mathematical structures actually the same? If one system uses a precise equation and the other uses a philosophical statement, similarity of theme is not enough. Second, is there evidence of historical transmission? If one tradition influenced another, there may be texts, translations, teachers, travelers, institutions, or documented intellectual contact. Without such evidence, independent resemblance is more cautious than direct lineage. Third, did the older claim make a specific prediction? A scientific prediction is valuable because it risks being wrong. It identifies what should happen under particular conditions. A statement that can be interpreted to fit almost any outcome does not carry the same risk. These questions are simple, but they change the mood of the investigation. The listener no longer asks only, "Does this sound similar?" The listener asks, "How similar is it, and in what sense?" That shift turns skepticism into a form of curiosity. Instead of destroying the mystery, it reveals layers. Some comparisons collapse immediately, others survive as metaphors. A few may reveal genuine historical influence. Still others show that different cultures independently confronted similar philosophical problems. Each outcome is interesting for a different reason. The danger appears when all outcomes are called validation. Validation is a strong word. It suggests that one body of knowledge has been tested by another and shown to be correct. But modern particle physics cannot validate a broad ancient philosophy merely by using language that resembles it. Nor can a philosophical resemblance validate a modern scientific theory. The relationship is more complicated. Science may inspire new readings of old texts. Old philosophy may inspire new questions about the meaning of scientific concepts. Mathematics may provide formal tools that neither side anticipated. These conversations can be valuable without becoming proofs. In fact, they may become more valuable once the pressure to prove ancient superiority is removed. An old philosophical idea can be profound because it changed the way people understood experience. A modern physical theory can be profound because it predicts experimental outcomes with extraordinary accuracy. They do not need to compete for the same kind of authority. This method requires patience, yet it offers a greater reward. It lets the audience keep the wonder while seeing where it comes from. Sometimes the surprise is a mathematical connection. Sometimes it is a historical exchange. Sometimes it is simply the human mind returning to the same questions about change, order, knowledge, and reality. Those outcomes should not be flattened into one story, because each reveals a different kind of relationship between the past and the present. A careful listener can therefore remain open without becoming credulous, and skeptical without becoming dismissive. The goal is not to protect modern science from ancient wisdom, or ancient wisdom from modern science. It is to let each speak clearly enough that any real connection has a chance to be recognized. This distinction prepares the story for its most controversial comparison. The word observer appears in quantum mechanics. To ordinary ears, an observer is a conscious person. Ancient contemplative traditions have spent centuries studying consciousness. The bridge seems almost perfect. If observation matters in quantum physics, perhaps consciousness creates physical reality. If meditation investigates consciousness, perhaps ancient contemplatives discovered the mechanism long before laboratories existed. This claim appears everywhere because it combines two of the deepest mysteries humans know, the mystery of matter and the mystery of awareness. But once again, the crucial question is hidden inside a word. What does observer actually mean in the context of quantum measurement? Does the theory require a conscious human mind, or has ordinary language quietly imported a conclusion that the mathematics itself does not demand? The next chapter enters that confusion very carefully. There, the documentary will discover something surprising. Removing the exaggerated claim that consciousness magically creates reality does not make quantum measurement ordinary. The real measurement problem remains strange enough without the myth, and perhaps that is the pattern emerging through the entire investigation. Whenever an easy, mystical answer is removed, a deeper and more difficult mystery appears underneath it. Few words in quantum physics have caused more confusion than observer. In ordinary language, An observer is a person who watches. Someone stands beside an event, looks at it, and becomes aware of what happened. The word carries consciousness inside it almost automatically. So when people hear that observation matters in quantum mechanics, a dramatic conclusion seems to follow. Perhaps consciousness creates reality. Perhaps the universe remains undecided until a human mind looks. Perhaps ancient contemplatives, who spent centuries studying awareness, had already discovered the deepest secret of modern physics. The story is powerful because it connects two mysteries that already feel almost impossible on their own. What is matter and what is consciousness? Bring them together, and the result seems capable of explaining everything. But the word observer is doing too much work. In quantum mechanics, measurement involves physical interactions, experimental arrangements, mathematical states, and definite outcomes. A detector can register an event. An apparatus can interact with a system. The theory raises profound questions about how the mathematical description relates to the results that experiments actually produce. None of this automatically requires a conscious human mind to perform a magical act of creation. Different interpretations of quantum mechanics offer different accounts of what is happening. Some emphasize collapse, others avoid collapse in the traditional sense. Some focus on information, relationships, histories, or branching descriptions. The debate is not settled by simply saying consciousness. This is important because popular explanations often move through several steps without showing them. First, measurement matters. Then measurement becomes observation. Observation becomes a conscious observer. The conscious observer becomes the cause of a physical outcome. Finally, ancient meditation is presented as experimental proof because meditation studies consciousness. Each step may sound natural in ordinary language. Together, they create a conclusion the mathematics has not established. Yet removing that conclusion does not make the quantum measurement problem disappear. This is the surprise. The real problem is still there. Quantum theory can describe a range of possible outcomes and assign probabilities to them with extraordinary accuracy. Experiments produce definite records. How the formal description should be understood in relation to those definite outcomes remains one of the deepest conceptual questions in the foundations of quantum mechanics. The mystery is genuine. It simply may not be the mystery popular culture prefers. There is something psychologically revealing about this difference. People often want a difficult mystery to end in a familiar subject. Consciousness feels familiar because everyone experiences it directly, even if no one fully understands it. By placing consciousness at the center of quantum mechanics, the unknown world of particles suddenly seems connected to the most intimate fact of existence. I am aware. Therefore, perhaps my awareness shapes reality. The thought is difficult to resist, but scientific explanation cannot be built from emotional attraction alone. If consciousness is claimed to play a specific physical role, that role must be defined. The claim must show what counts as conscious observation, when it begins, what physical difference it makes, and how the prediction differs from theories that do not require consciousness. Without that precision, the idea remains philosophical speculation rather than established physics. This distinction also protects contemplative traditions from being reduced to a fashionable scientific slogan. Meditation and introspection can explore attention, perception, thought, emotion, and the structure of experience. These practices may offer valuable insights into how the mind constructs a world of meaning. But that is not the same as operating a particle detector. A contemplative practitioner does not validate a quantum equation by becoming deeply aware. A physicist does not solve the nature of consciousness by measuring a photon. The mysteries can touch without becoming one mystery. That may be the more honest meeting place. The word observer reveals how easily language can create a bridge before evidence has built one. It also reveals a deeper pattern running through the documentary. Zero sounded like nothing, until several kinds of nothing were separated. Connection sounded like unity, until different kinds of relation were defined. Observer sounds like consciousness, until the physical role of measurement is examined. Again and again, the mystery becomes clearer when a familiar word is opened and inspected. For the late-night listener, this produces a strange calm. There is no need to rush toward a final metaphysical answer. The unresolved problem is already large enough. A theory can predict experimental outcomes with astonishing precision, while leaving room for disagreement about what the mathematical description says reality is doing. Physics, at its deepest edge, can be both successful and conceptually unsettled. That is far more interesting than a simple slogan. It means knowledge can advance without every philosophical question being closed. It means people can build technologies using quantum theory while still debating the best way to understand its foundations. And it means the boundary between what can be calculated and what can be pictured remains one of the central tensions of modern science. In other words, removing a myth does not leave an empty space. It reveals a boundary between calculation and interpretation, between what experiments establish and what philosophy debates. That boundary is not a weakness. It keeps the unanswered question visible clearly. This is where quantum monasticism begins to take on a more serious meaning. Not as a claim that monks secretly discovered wave functions, not as a claim that meditation collapses quantum states, but as a metaphor for disciplined uncertainty. The physicist must learn to resist common sense when the experiment disagrees. The contemplative must learn to question immediate impressions when the mind reveals its own instability. Their methods remain different. Their standards of evidence remain different. Yet both confront the possibility that appearances are not the final structure of reality. The next section will enter that quieter territory. It will place the monastery and the laboratory beside each other without pretending they are the same institution, and ask whether their most meaningful connection lies not in a secret equation, but in the humility required when certainty begins to fail. Imagine 2 rooms at night. In one, a physicist sits before a screen filled with data. The experiment has been repeated. The instruments have been calibrated. Errors have been estimated. The result is not what intuition expected. In the other, a contemplative practitioner sits in silence. Attention returns again and again to experience. Thoughts appear, sensations change. Certainties that felt solid begin to look more temporary when watched closely. The 2 people are not performing the same experiment. They do not use the same methods. They do not produce the same kind of evidence. Yet both are practicing a form of discipline against assumption. The physicist cannot keep a preferred theory merely because it feels elegant. If the measurements repeatedly disagree, something must change. The contemplative cannot assume every thought is true merely because it appears vividly. The practice itself may reveal how quickly the mind constructs stories, identities, fears, and expectations. This is where the metaphor of quantum monasticism becomes useful. It does not describe a lost ancient school. It describes an attitude: withdraw from noise, attend closely, repeat the method, question the obvious, accept that reality may not match the first story the mind tells about it. This attitude appears in many forms of serious inquiry. A mathematician may spend months following a proof because one unsupported step can destroy the whole structure. A historian may abandon a beautiful narrative when the documents refuse to support it. A scientist may repeat an experiment because one surprising result is not enough. Discipline is often less dramatic than revelation, but it is what keeps revelation from becoming fantasy. The monastery and laboratory, therefore, meet most honestly at the level of humility. Both can expose the limits of ordinary perception. Both can reveal that the mind prefers certainty even when certainty is not available. Both can require patience with results that are uncomfortable. But the similarities end if they are stretched too far. Scientific claims must be publicly testable. Other researchers must be able to examine the method, challenge the result, and attempt replication. A physical theory gains authority because it survives repeated confrontation with evidence. Contemplative insight belongs to a different kind of inquiry. It can be systematic, disciplined, and transformative, but its relationship to public measurement is not identical to that of particle physics. To say this is not to rank one above the other. It is to prevent confusion. A thermometer and a meditation practice answer different questions. A detector and an introspective report belong to different evidential systems. They may inform a larger philosophical conversation, but one cannot automatically certify the other. This distinction becomes especially important when people claim that ancient spiritual traditions have been proven by quantum mechanics. What exactly has been proven? A physical correlation? A mathematical symmetry? A claim about consciousness? A teaching about the self? Without precision, the word proven becomes as slippery as observer. The stronger approach is to allow conversation without pretending identity. Modern physics can challenge naive ideas about matter. Contemplative traditions can challenge naive ideas about the stability of experience. Philosophy can ask what these challenges mean. Mathematics can provide structures that make physical prediction possible. History can show how each tradition actually developed. Each field contributes something different. The result is not a single ancient secret. It is a network of questions. And perhaps that is why the subject remains so compelling at night, when the demand for immediate answers grows weaker. A listener can hold uncertainty without feeling that the story has failed. What is real before measurement? What is the relationship between a model and the world it describes? How much of ordinary experience is shaped by the categories the mind brings to it? These questions do not collapse into one equation, but they can illuminate each other. The physicist and the contemplative both discover, in different ways, that the first appearance of a thing may not reveal its deepest structure. A solid object becomes a quantum system described through fields and probabilities. A fixed self may become, under introspection, a changing stream of sensations, memories, and thoughts. Again, the analogy must remain an analogy, but it is a meaningful one. Both journeys reduce confidence in surface appearances. Both require new languages when ordinary language becomes inadequate. Both can leave the practitioner with more humility than certainty. This humility may be the most valuable bridge between ancient contemplative culture and modern physics. It does not claim that a monk discovered the standard model. It does not claim that a physicist has confirmed a spiritual doctrine. It suggests only that serious inquiry, wherever it occurs, often begins by learning how easily the mind mistakes familiarity for truth. There is a lesson in this comparison. The mind wants one language to explain every mystery at once. Physics is asked to prove spirituality. Spirituality is asked to complete physics. Ancient texts are asked to anticipate modern laboratories, while modern laboratories are asked to certify meanings their instruments were never designed to test. The result is a grand unified story, but not necessarily a true one. A more careful approach accepts that different methods illuminate different parts of human experience. Their boundaries can be frustrating, yet those boundaries are precisely what allow each method to remain reliable. When the borders are respected, conversation becomes possible without confusion, and resemblance can be appreciated without being promoted into evidence. From here, the story moves toward another word that has escaped its technical boundaries and entered popular mythology: entanglement. In laboratories, entanglement refers to specific quantum relationships with measurable consequences. In popular imagination, it becomes proof that everything is connected to everything else. From there, it becomes cosmic unity, telepathy, destiny, and spiritual oneness. The movement happens so quickly that the original scientific meaning can disappear. The next chapter will slow that movement down. It will ask what entanglement actually shows, what it does not show, and why the real phenomenon is stranger than the mystical slogan that has grown around it. The word entanglement sounds mysterious, even before anyone explains it. It suggests threads, knots, invisible bonds, and things that cannot be separated cleanly. In quantum physics, the term refers to a specific kind of relationship between systems. When quantum systems are prepared or interact in certain ways, the mathematical description of the whole cannot always be reduced to two completely independent descriptions of the parts. Measurements made on entangled systems can produce correlations that defy certain classical expectations. This is not a poetic claim. It is something physicists can test. Experiments inspired by Bell's theorem have examined whether the correlations predicted by quantum mechanics can be explained by broad classes of local hidden variable theories. The results have repeatedly supported the quantum predictions and ruled out those simple classical alternatives under the tested conditions. For the history of physics, this is extraordinary. For popular culture, it becomes something else almost immediately. Everything is connected. The phrase is simple, memorable, and emotionally satisfying. It seems to confirm ancient teachings of unity. It appears to offer a scientific foundation for spiritual oneness. In more extreme versions, it is used to support claims about telepathy, distant healing, manifestation, destiny, or a universal consciousness linking every mind. The scientific term has crossed into mythology. But what happened during the crossing? First, a precise quantum relationship became a general idea of connection. Then connection became influence. Influence became communication. Communication became conscious communication. Finally, consciousness became cosmic unity. Each step adds a new claim. The original experiment does not automatically supply those additions. This is where the real phenomenon must be protected from its own popularity. Entanglement is already strange. It does not need telepathy to become interesting. The correlations predicted by quantum theory challenge the idea that every measurement result can be explained by local pre-existing properties in the simple way classical intuition might suggest. That alone is enough to disturb familiar pictures of reality. Yet quantum entanglement does not allow people to use the effect as an ordinary faster-than-light messaging system. The correlations have a precise structure. They are not a blank check for every form of mysterious influence. The difference matters because the phrase, "everything is connected," hides the most important question. Connected how? A family is connected through relationships. Cities are connected by roads. Computers are connected by networks. Events can be connected by cause. Mathematical quantities can be correlated. Quantum systems can be entangled. The word connection changes meaning across each example. To place them all under one label creates emotional unity but explanatory confusion. Ancient philosophical traditions that speak of unity may be making claims about existence, consciousness, identity, dependence, or spiritual experience. Quantum entanglement makes a claim within a mathematical physical theory. The two may inspire comparison. They are not automatically equivalent. Again, the question of prediction becomes useful. Did an ancient statement specify the mathematical form of quantum correlations? Did it identify experimental conditions under which a Bell-type inequality would be violated? Did it distinguish quantum entanglement from ordinary shared causes or classical correlation? If not, then the resemblance belongs to analogy rather than scientific anticipation. This conclusion may disappoint anyone hoping for a simple proof that ancient philosophy predicted modern physics. But the disappointment does not last long if the real science is allowed to speak. Entanglement suggests that classical separability is not always a sufficient guide to quantum systems. The whole can contain relational information that is not captured by treating the parts as though they carried completely independent local descriptions of the ordinary kind. That is a profound idea. It asks the mind to loosen its grip on the image of reality as a collection of separate objects, each possessing a complete set of familiar properties waiting to be revealed. No mystical addition is required. The mystery is already present in the mathematics and the experiments. This is becoming a recurring pattern in the documentary. The popular version is often more dramatic but less precise. The scientific version is narrower but, once understood, more unsettling. A slogan says, "Everything is connected." The experiment asks what kinds of correlations nature permits and what classical explanations fail. The slogan seems larger. The experiment reaches deeper. There is another reason entanglement attracts spiritual interpretation. It appears to violate the ordinary intuition that distant things should possess fully separate stories. The mind hears that and reaches immediately for older languages of wholeness. Yet the scientific result is more disciplined. It concerns correlations predicted by a particular mathematical framework and observed through carefully chosen measurements. That precision matters because mystery grows weaker when every kind of connection is treated as interchangeable. A friendship is not a quantum state. A shared memory is not entanglement. Two people thinking of each other at the same moment is not, by itself, evidence of a Bell-type correlation. The real achievement of quantum experiments is not that they confirm every intuition about unity, but that they identify a specific boundary beyond which certain classical explanations fail. The boundary is narrow enough to be tested, and that is exactly what gives it power. The mystery becomes stronger when its limits are known, because those limits show exactly where ordinary explanations stop working today. For a late-night audience, this distinction creates a different kind of suspense. The question is not whether physics has proven every ancient statement about unity. The question is why nature contains relationships that force human beings to abandon some of their most comfortable assumptions about separateness. And once that question appears, another mystery follows. Why are people so eager to turn a precise scientific result into a universal spiritual confirmation? Why does the mind prefer the grand story? Why do similarities feel like proof, even when the steps between them are missing? The next section turns the investigation inward. It leaves the particle detector for a moment and examines the pattern-finding mind itself, because the same human ability that discovers genuine structure can also build bridges across gaps where no demonstrated connection exists. Human beings are pattern-making creatures. A face is recognized from a few lines. A familiar song is identified from the opening notes. Footprints in mud suggest that someone passed by. Dark clouds suggest rain. This ability is not a flaw. It is one of the foundations of intelligence. Science depends on it. Mathematics depends on it. History depends on it. A researcher notices a regularity and asks whether it can be measured. A mathematician notices a relationship and asks whether it can be proved. A historian notices a similarity and asks whether there is evidence of influence. The problem begins when the mind forgets that a noticed pattern is only the first step. A resemblance can be real without being causal. Two traditions can develop similar ideas independently. Two sentences can sound alike while referring to different things. Two mathematical methods can produce similar effects while using entirely different structures. Because the human brain prefers coherence, it often completes the story before the evidence does. This is especially likely when the story is emotionally rewarding. The claim that ancient thinkers anticipated modern physics offers several rewards at once. It challenges modern arrogance. It gives the past hidden power. It turns history into a mystery. It suggests that wisdom was lost rather than absent. Once a person wants that story to be true, every resemblance begins to shine more brightly. The documentary therefore needs a simple map. There are at least three different kinds of connection. The first is historical connection. This requires evidence that ideas moved between people, texts, schools, regions, or periods. A translation may survive. A traveler may describe what was learned. A teacher may name a source. A chain of influence may be reconstructed. The second is mathematical equivalence. Here, two formulations can be shown to share the same structure in a rigorous sense. The connection is not based on mood or vocabulary. It can be demonstrated step by step. The third is analogy. An analogy says that two things resemble each other in a useful way. A wave in water may help someone imagine a wave in another context even when the underlying physics is different. A network may help explain relationships that are not literally wires. A philosophical idea may offer language for thinking about a scientific concept without becoming the concept itself. Analogy is powerful, but it is not proof. Many ancient quantum claims begin as analogies and quietly change category. A person notices that an old text speaks of unity. Quantum physics contains entanglement. The two are compared. Then the comparison is described as anticipation. Finally, anticipation becomes validation. At no point is the missing mathematical or historical bridge supplied. The language becomes stronger while the evidence remains the same. This is one of the most important psychological mechanisms in the entire story. It explains how sincere people can become convinced without deliberately inventing anything. The pattern feels meaningful. The story feels coherent. The conclusion arrives naturally. Only later does someone ask whether each step was justified. Skepticism, in this sense, is not the enemy of wonder. It is the second stage of pattern recognition. The first stage says, "I see a connection." The second asks, "What kind of connection is it?" That question can deepen the mystery. A historical link may reveal forgotten exchanges between cultures. A mathematical equivalence may reveal that two apparently different problems share one structure. An analogy may reveal a universal human concern, even without direct influence. Each discovery is valuable. The mistake is insisting that every resemblance must be the strongest possible connection. The pattern-making mind also has another habit. It remembers the successful matches more vividly than the failed ones. A statement that can be connected to a modern discovery is repeated, while dozens of statements that do not match are forgotten. Over time, the surviving examples create the appearance of extraordinary accuracy. This does not require dishonesty. It can happen naturally through selective attention and memory. The remedy is not cynicism, but comparison. Ask how many possible interpretations existed before the discovery. Ask whether the same text has been linked to several different modern ideas in different decades. Ask whether a prediction was specific enough to fail. These questions do not close the door on ancient insight. They simply make sure the door is attached to a wall, rather than floating freely in imagination. Once that standard is accepted, the investigation becomes calmer, more exact, and surprisingly more rewarding. A careful standard does not silence wonder. It prevents wonder from being mistaken for evidence before the evidence has even arrived. This is where the 16 sutras return to the center of the documentary. They have remained in the background while the story explored ancient mathematics, quantum theory, symmetry, zero, observation, and entanglement. Now they must face a more direct test. What do the methods actually do? How do they simplify calculation? What mathematical structures do they use? And when those structures are compared with the mathematics of modern particle physics, does a specific technical bridge appear? This test is important because it removes the protection of broad language. Words such as unity, pattern, and transformation can stretch across many subjects. Actual mathematics is less flexible. A formula has a defined operation. A symmetry has a defined structure. A physical theory makes particular predictions. Once the comparison reaches that level, resemblance must become precise or disappear. The result may not satisfy those hoping for a lost quantum code, but it may reveal something more durable. Perhaps the value of the sutras is not that they secretly describe particles. Perhaps their relevance lies in the broader mathematical instinct to reorganize a problem until hidden simplicity appears. That is the question waiting in the next chapter. The sutras are about to be placed beside quantum field theory, not as symbols of ancient wisdom, but as mathematical objects whose actual operations can be examined. And once the poetry is removed, the documentary can finally ask whether the strongest claim survives. The strongest claims should be tested at their strongest point. For most of the documentary, the phrase Vedic mathematics has remained surrounded by history, philosophy, and broad comparisons about pattern. Now the atmosphere must become simpler. Forget the mystery for a moment. Look at the methods. The techniques popularized under the name Vedic mathematics are commonly presented as computational strategies. They reorganize arithmetic or algebraic problems, exploit numerical relationships, use complements, factorization, or pattern recognition, and in some cases reduce the amount of written work needed to reach an answer. This can be impressive. A student who expects a long calculation may discover a shorter path. A mental calculator may recognize a structure that allows several steps to be combined. The method can feel elegant because it reveals order in a problem that initially looked messy. But particle physics is asking a different kind of question. The mathematics used in modern quantum field theory includes structures developed for describing fields, probabilities, amplitudes, symmetries, transformations, and interactions. The Standard Model is not a collection of mental arithmetic shortcuts. It is a physical theory whose mathematical form is tied to experimental evidence gathered across generations. This difference is not a matter of cultural importance. It is a matter of mathematical content. A multiplication technique can be valuable without describing a quantum field. A rule for simplifying a class of algebraic expressions can be clever without predicting a particle. A computational procedure can be historically interesting without serving as the hidden foundation of modern physics. Once the comparison is made at the technical level, the strongest literal claim begins to weaken. There is no demonstrated path by which the 16 sutras of the modern Vedic mathematics system generate the Standard Model. They do not provide the specific field equations used by particle physicists. They do not reproduce the experimental framework through which elementary particles were identified. They do not become gauge theory simply because both subjects use mathematics. This conclusion may sound obvious when stated plainly, yet it is rarely how the mystery is presented. Popular claims often remain at the level of words such as pattern, energy, vibration, unity, and transformation. Those words are flexible enough to create an atmosphere of similarity. Mathematics is less forgiving. An operation either matches another operation in a demonstrable way, or it does not. A structure either has the required properties, or it does not. A prediction either follows from the method, or it must be imported from somewhere else. This is why placing the sutras on trial does not mean disrespecting them. It means allowing them to stand as mathematics rather than mythology. If a method is useful, its usefulness can be shown. If it is efficient for certain problems, that can be demonstrated. If its historical origin is disputed, that dispute can be examined separately. None of those questions requires quantum physics, and none becomes more true by borrowing the prestige of quantum physics. There is also a historical benefit to this stricter comparison. Once the pressure to prove quantum ancestry is removed, the computational methods can be discussed without forcing them to carry a civilization-sized claim. Their strengths can be taught, their limits can be tested, their origins can be debated, using documents rather than reverence in a serious historical investigation. That is a healthier form of respect, because it allows the mathematics to succeed or fail on its own terms. It also prevents a familiar mistake in forbidden knowledge stories, assuming that anything impressive must have been hidden because ordinary human development seems too slow or too simple to satisfy the imagination. Something surprising happens once this is accepted. The connection does not disappear entirely. It changes level. The direct claim asks whether the sutras contain modern particle physics. The better question asks why reorganizing a problem can reveal hidden simplicity. That question belongs to mathematics everywhere. A difficult problem is often difficult partly because of its representation. Change the representation, and the structure may become visible. A polynomial can be factored. A geometric problem can be transformed. A physical system can be expressed in variables that make a symmetry easier to see. A computation can be rewritten so that repeated work disappears. These examples are not identical, but they share a broad lesson. How a problem is written affects how difficult it appears. This lesson is far more durable than the claim of a hidden quantum code. It also fits the larger journey of the documentary. Ancient geometry taught that a relationship could survive the disappearance of the original drawing. Modern physics showed that mathematical structure could remain reliable when ordinary pictures failed. Symmetry revealed that transformations could expose what remains invariant. The debate over zero showed that definitions determine what a concept can legitimately mean. Now the sutras contribute another piece. Representation matters. The right form can make hidden structure easier to see. This does not make all forms equivalent. A useful arithmetic representation does not automatically become a physical theory, but the habit of searching for a better representation is shared across mathematics. That may be the strongest legitimate bridge available. It is not ancient prediction. It is mathematical instinct. The instinct says that complexity may contain structure. The structure may be exposed by transformation, and once exposed, the problem can appear almost shockingly simple. For the mystery-loving listener, this conclusion is less sensational than the idea of forgotten quantum knowledge, but it carries a more unsettling implication. What if some of the hardest problems in nature seem impossible only because the correct language has not yet been found? What if a future theory will make today's complicated mathematics look like a clumsy first draft? What if the deepest advances come not from discovering more pieces, but from learning to describe the same pieces differently? Those questions belong to modern physics as much as to mathematics, and they lead directly into the dream of compression. The hope that a small number of principles can generate a world of overwhelming complexity. The history of mathematics is filled with moments when many separate steps become one rule. A repeated calculation becomes an algorithm. A family of examples becomes a theorem. A collection of observations becomes an equation. The shorter description feels powerful because it does more with less. This is compression in the broad intellectual sense. It does not mean squeezing information carelessly until detail is lost. It means finding a structure that preserves what matters while removing repetition. The dream is ancient and modern at once. Find the rule beneath the cases. Find the pattern beneath the noise. Find the transformation that turns a long path into a short one. This is part of the appeal of sutra-like mathematics. A compact statement can guide many calculations. The rule seems small, yet its reach may be large. Modern physics has its own version of this dream. Physicists search for principles capable of organizing many phenomena at once. A successful theory should not merely describe one experiment. It should connect results, restrict possibilities, and reveal relationships that were previously hidden. The Standard Model does this remarkably well within its domain, but it is not the final story of physics. Questions remain about gravity, dark matter, the pattern of particle masses, and other unresolved problems. So the search for deeper structure continues. Some physicists hope that apparently separate features of nature may emerge from a more unified framework. Others explore new mathematical languages. Experiments search for deviations that might reveal where current theories break down. Behind these efforts lies a familiar hope. Perhaps there is a simpler description. But simplicity is dangerous when loved too much. Human beings often assume that nature must be elegant, because elegant theories are beautiful to the human mind. Nature has made no such promise. A simple theory may be wrong. A complicated theory may describe reality better. A pattern may exist only because a small sample makes randomness look organized. This is where compression must remain disciplined. A shorter explanation is valuable only if it preserves the facts. A beautiful equation is valuable only if its predictions survive experiment. A clever shortcut is valuable only if it produces the correct result in the cases where it is used. The rule cannot be judged by beauty alone. This lesson separates mathematical elegance from mystical certainty. A mystical claim can remain attractive even when no test is available. A scientific claim must risk failure. That risk is what gives successful compression its authority. When a compact theory survives thousands of opportunities to fail, its simplicity becomes meaningful. It has not merely pleased the mind, it has endured contact with the world. Compression also changes the way knowledge feels. A long list of facts can be remembered, but a principle can be understood. Once the principle is seen, many facts become consequences rather than isolated burdens. This is why elegant explanations can create an almost physical sense of relief. The mind stops carrying each case separately. It sees one structure moving through them all. Yet that emotional relief can become a trap. A person may accept a simple explanation because it feels complete, even when important details have been discarded. The discipline of mathematics and science is therefore not merely to simplify, but to simplify without cheating. Every discarded detail must truly be unnecessary. Every claimed pattern must survive cases that were not chosen to make it look good. Only then does compression become understanding instead of decoration. This is why the strongest connection between sutra-like methods and modern physics is not a claim of common origin. It is a shared aspiration toward economical description. Both can reward the discovery that a problem contains hidden structure. Both can create the experience of complexity collapsing under the right transformation. But they operate in different domains and answer different questions. The distinction should remain visible, otherwise the beauty of one is used as evidence for the history of the other. The deeper philosophical question is more interesting. Why should compression be possible at all? Why can a small set of mathematical rules describe so much? Why does the universe contain regularities stable enough for laws to exist? A world of pure chaos would not reward mathematics in the same way. A world in which every event followed a completely unrelated rule would resist generalization. Yet human beings repeatedly discover patterns that apply across enormous ranges of space and time. The same physical laws used in a laboratory can describe light from distant stars. The same mathematical structure can appear in problems that look unrelated on the surface. This success tempts the mind toward metaphysics. Perhaps reality is mathematical. Perhaps mathematics is only the language humans invented to describe regularity. Perhaps the fit between mind and world is a consequence of evolution, selection, and the way useful abstractions are retained. Or perhaps the effectiveness of mathematics points toward something deeper that remains philosophically unresolved. The documentary does not need to choose among those possibilities. It only needs to notice the mystery. Once the literal claim of ancient quantum prediction weakens, this larger question comes into focus. The real bridge may not run from a Vedic sutra to a particle equation. It may run through the human desire to compress experience into structure. That desire appears whenever people search for laws, algorithms, patterns, and symmetries. It can produce great science. It can also produce false certainty. The difference lies in testing. A pattern that survives testing becomes knowledge. A pattern that merely feels right remains a possibility. This brings the documentary to its final human puzzle. If the strongest evidence does not support the claim that modern particle physics directly validates Vedic mathematics as an ancient quantum system, why is that claim so attractive? Why do people across cultures return again and again to stories in which the ancients knew what modern science has forgotten? The answer has less to do with equations than with memory, pride, loss, and the emotional power of forbidden knowledge. Stories of lost knowledge rarely survive because of evidence alone. They survive because they satisfy something emotional. A forgotten civilization that knew more than modern science is not merely a historical possibility, it is a reversal. The present, which assumes itself advanced, becomes the student. The past, which textbooks may have simplified, becomes the keeper of secrets. For many cultures, that reversal carries real weight. History has not always been told fairly. Civilizations outside Europe have often had their achievements minimized, misunderstood, or reduced to a few familiar examples. Colonial systems sometimes treated conquered peoples as intellectually inferior, while benefiting from knowledge that had developed in those societies long before colonial rule. Against that background, claims of ancient scientific greatness can feel like restoration. They say, "You were wrong to dismiss them. They knew more than you admitted. Perhaps they knew more than you know now." The emotional movement is understandable, but it creates a danger. In trying to restore dignity to the past, people may begin assigning the past achievements it did not actually make. Ancient Indian mathematics does not need a hidden particle accelerator to be important. Its real history already contains sophisticated work in geometry, calculation, astronomy, number systems, and algebraic reasoning across many centuries. Those achievements become harder to appreciate when every discussion is pulled toward the claim that the ancients secretly knew quantum physics. The modern theory then becomes the standard by which the ancient world is judged. Instead of asking what an ancient mathematician discovered, the question becomes whether the discovery resembles something modern enough to impress us. This is a subtle form of disrespect. It says the past matters only when it can be made to look like the present. The irony is deep. A myth created to honor a civilization can erase the civilization's actual intellectual world. Ritual geometry becomes quantum geometry. Astronomical calculation becomes space science in the modern sense. Philosophical reflection becomes particle theory. The older meanings disappear under new labels. Forbidden knowledge stories are especially vulnerable to this transformation. Their structure rewards exaggeration. A normal historical development is less exciting than a suppressed discovery. A clever method is less dramatic than a lost technology. A philosophical parallel is less clickable than the claim that scientists are finally admitting the ancients were right. The stronger the claim becomes, the easier it is to tell as a mystery. But a documentary can create mystery without sacrificing history. The real questions are powerful enough. How did mathematical abstraction develop in different cultures? Why did certain ideas appear earlier in some places than others? How did knowledge travel? What was preserved, translated, forgotten, rediscovered, or independently invented? Why do modern readers reinterpret old texts through new scientific language? These questions contain genuine uncertainty. They do not need a conspiracy to become fascinating. There is also a psychological reason lost knowledge stories feel comforting. If knowledge was once possessed and then forgotten, the universe seems less unknown. Someone already had the answer. The problem is only recovery. That is easier to accept than the possibility that no civilization has ever known the final answer, and that humanity is still standing near the beginning of understanding. Lost knowledge promises that truth is behind us, hidden in ruins and manuscripts. Science often suggests that truth may still be ahead, beyond experiments not yet built and mathematics not yet invented. The first story offers nostalgia, the second requires patience. For a late-night audience drawn to forbidden mysteries, the tension between them is irresistible. Imagine that an ancient text contains a sentence that sounds strangely modern. The immediate reaction is wonder. The second reaction is suspicion. Why were we never taught this? Was the knowledge ignored? Was it suppressed? Did modern science borrow from it without acknowledgement? Sometimes such questions uncover genuine histories of neglect or transmission. Sometimes they reveal only that the modern interpretation was added later. The responsible storyteller must remain open to both possibilities. There is one more reason the forbidden knowledge frame is so durable. It turns uncertainty into injustice. Instead of saying that historians do not know, the story says someone hid the answer. Instead of saying claim lacks evidence, it says the evidence was suppressed. This move is satisfying because it gives the mystery a villain, yet it can also make the claim impossible to test, since every missing document becomes proof of concealment. A documentary must resist that trap. Suppression has happened in history, but it must be demonstrated like any other claim. Otherwise, absence becomes evidence for whatever story the audience prefers, and the mystery can never be corrected by facts. This is why the documentary has spent so much time separating categories. Ancient achievement is real. Modern Vedic mathematics has a particular 20th century history. Quantum physics has a specific experimental and mathematical foundation. Philosophical parallels can be meaningful. None of those facts requires the others to be false. The error begins when they are compressed into one heroic legend. A more respectful story allows the ancient world to remain different. Its people asked questions that mattered to them. They developed techniques suited to their problems. They built traditions whose value does not depend on whether a modern laboratory later used the same vocabulary. This kind of respect is quieter. It does not produce the easy thrill of saying everything was known thousands of years ago. But it offers something better. It allows discovery to happen twice. First, the listener discovers what the past actually achieved. Then the listener discovers why the modern imagination wanted the past to have achieved something else. Both stories reveal hidden assumptions, and together they prepare the final question. The title of this documentary claims that modern particle physics is validating ancient Vedic mathematics. After 9 chapters, almost every word in that sentence has changed meaning. The next section will put the title back together piece by piece and ask which part survives once history, mathematics, psychology, and scientific evidence are all placed on the same table. Return to the title slowly. Quantum monasticism: why modern particle physics is validating ancient Vedic mathematics. At the beginning, the words seem to form one clear claim. Now each word carries a warning. Quantum refers to a modern scientific framework developed to describe phenomena that classical physics could not explain. It is mathematical, experimental, and extraordinarily successful within the domains where it has been tested. Monasticism, in this documentary, has become a metaphor rather than a historical assertion. It describes disciplined attention, withdrawal from assumption, and the patience required to remain with difficult questions. Modern particle physics refers to a specific body of theory and experiment, including quantum field theory and the Standard Model. Its authority comes from mathematical consistency joined to observation. Ancient Indian mathematics refers to a long and varied history that cannot be reduced to one book or one set of techniques. Vedic mathematics, as the term is commonly used today, refers to the system associated with Bharati Krishna Tirtha and the 16 sutras presented in the 20th century, whose direct derivation from the ancient Vedas is disputed. Then there is the final word, validating. That word has carried the entire mystery. To validate something scientifically is not merely to resemble it. A modern theory does not validate an ancient statement, because both can be described with the word unity. A quantum experiment does not validate a philosophical teaching, because both raise questions about observation. A mathematical symmetry does not validate a computational shortcut, because both reduce complexity. Validation requires a closer relationship. The claim being validated must be specific enough to test. The modern result must bear directly on that claim. The connection must survive definitions rather than depend on flexible language. By that standard, the strongest version of the title does not survive. Modern particle physics does not demonstrate that the 16 sutras of Vedic mathematics contain quantum field theory. It does not show that ancient Vedic texts predicted the Standard Model. It does not establish a historical chain from those sutras to the mathematics used in modern particle laboratories. If the documentary ended here, the conclusion would be simple. The title was too strong. But something remains. Modern physics demonstrates, with extraordinary force, that abstract mathematics can reveal structures far beyond ordinary perception. Ancient mathematical traditions demonstrate that human beings have long developed methods for separating relationship from object, rule from example, and pattern from surface appearance. The modern Vedic mathematics tradition demonstrates the appeal of compact procedures and alternative representations that can make certain calculations easier. These are not the same achievement, yet they resonate around a common human instinct. Look beneath complexity, search for a pattern, transform the problem, find what remains. This instinct is not uniquely Vedic, uniquely modern, or uniquely scientific. It appears throughout the history of mathematics. It is one of the reasons mathematics can grow. A problem solved once becomes a method. A method becomes a general rule. A rule becomes part of a larger structure. The structure reveals new questions. The resemblance between ancient and modern thought therefore survives, but at a different level from the one promised by the title. It is not validation, it is resonance. That word is weaker scientifically and stronger philosophically. Resonance allows two ideas to illuminate each other without claiming they are identical. It allows a modern physicist and an ancient mathematician to share a broad human search for order without inventing a direct line of transmission. It allows a contemplative tradition to ask profound questions about perception without being rewritten as quantum mechanics. It allows history to remain history, The change from validation to resonance also changes the tone of the story. Validation points in one direction, one system judges another and confirms it. Resonance is more balanced. It allows similarities to be explored while differences remain intact. A short rule may remind a physicist of mathematical economy. A symmetry may remind a philosopher that appearances can change while relationships persist. A contemplative practice may remind a scientist that human intuition has limits. None of these reminders creates a proof, but each can open a useful question. In this sense, the documentary does not need to choose between admiration and skepticism. It can admire ancient achievement, respect modern science, and remain skeptical of claims that confuse the two. The result is not less mysterious. It is simply a mystery whose boundaries are visible. A careful comparison can be generous without surrendering intellectual discipline. This may feel like the mystery has been reduced. In fact, it has been relocated. The original question was whether the ancients already knew what modern physicists know. The deeper question is why human beings, separated by culture and time, repeatedly discover that abstraction is so powerful. Why can a symbol stand in for an object? Why can a relationship survive when the object changes? Why can mathematics developed inside the human mind describe stars, atoms, fields, and particles? Why does the universe contain patterns stable enough to be discovered at all? These questions are not answered by proving that one tradition secretly contained another. They become visible only after that claim is set aside. This is the final reversal. The documentary began by asking whether modern science was validating ancient mathematics. It ends by asking whether the success of mathematics itself is the greater mystery. Perhaps the astonishing fact is not that old, and new ideas sometimes sound alike. Human beings use recurring metaphors. Cultures share basic experiences. Different thinkers can arrive at similar abstractions. The astonishing fact is that some abstractions work on nature. They predict, they survive testing, they reveal structures no eye can see. The final chapter will therefore give a verdict on the literal claim, then move beyond it. The historical question is almost closed. The philosophical question is opening. And somewhere between the monastery and the laboratory, the listener is left with a mystery larger than the one promised at the beginning. Why should reality be understandable through mathematics at all? The literal question can finally be answered. Modern particle physics does not validate the 20th century system commonly called Vedic mathematics as an ancient precursor to quantum theory. The standard model was not derived from the 16 sutras. Quantum field theory did not emerge from a hidden Vedic manuscript. The experimental discoveries that shaped modern particle physics were not confirmations of predictions found in those computational rules. The strongest version of the claim does not survive historical and mathematical examination. But the story does not end with the word no. A simple rejection would miss what the journey has revealed. The investigation began with two images: a modern detector searching for patterns inside particle collisions, and a scholar searching for order inside numbers. At first, the mystery seemed to depend on proving that one world had secretly anticipated the other. Now a different pattern has emerged. Across the history of mathematics, human beings repeatedly learn to move away from surface appearance and toward relationship. A line drawn on the ground becomes geometry. A group of objects becomes number. A repeated procedure becomes an algorithm. A changing shape reveals an invariant relation. A physical theory abandons a simple picture and trusts a mathematical structure that predicts what experiments will record. These developments belong to different times and different traditions. They are not one hidden lineage, yet they share a broad intellectual motion. The mind removes what seems accidental and searches for what remains. This is the pattern behind the pattern. It is not a secret formula. It is the human capacity for abstraction. That capacity allows people to reason about things they cannot hold. It allows a number to survive the disappearance of counted objects. It allows a geometric relation to survive the erasure of a drawing. It allows a physicist to calculate the behavior of a system that cannot be pictured as an ordinary mechanical object. The continuity lies there. Ancient mathematics did not need to contain quantum theory for its development of abstraction to belong to the same long human story that eventually made quantum theory possible. This is a more modest claim. It is also a stronger one. It does not depend on disputed chronology. It does not require a hidden transmission for which no evidence survives. It does not confuse analogy with mathematical equivalence. It simply recognizes that modern science stands at the end of a very long history in which human beings learned to trust symbolic relationships. That history belongs to many cultures. No single civilization invented the entire mathematical mind. Ideas emerged in different places, traveled across languages, were forgotten, rediscovered, translated, challenged, and improved. The modern world is built from that accumulated inheritance. To honor one tradition does not require erasing the others. And to celebrate ancient India does not require claiming that its scholars already possessed every later discovery. Their genuine achievements are enough. This conclusion opens a deeper question. If ancient and modern thinkers can both discover the power of abstraction, why does abstraction work so well? Why can mathematics leave ordinary experience behind and still return with accurate knowledge about the physical world? A mathematical object can be invented or discovered in a context that appears completely removed from nature, then decades or centuries later become useful in physics. A symmetry studied for its formal properties can help organize a theory of particles. A mathematical language can become the framework through which an experiment is understood. This effectiveness is so familiar to scientists that its strangeness can be forgotten. The equations work often enough that people begin to treat their success as normal. But it is not obviously normal. The universe could have been less regular. Human abstraction could have been too crude. The patterns accessible to the mind could have failed beyond the scale in which humans evolved. Instead, mathematical reasoning reaches from counting ordinary objects to predicting the behavior of matter at scales far beyond direct perception. That fact creates a mystery larger than the original title. Perhaps mathematics is successful because the human mind evolved inside a structured universe and learned to compress recurring patterns. Perhaps the mathematical structures exist independently and human beings gradually discover them. Perhaps mathematics is a language invented by minds but constrained so strongly by logic that it repeatedly finds the same deep forms. Different philosophies offer different answers. Physics does not settle the issue merely by succeeding. What it does show is that the fit is real enough to build experiments, technologies, and predictions around. The philosophical question remains open. This is where the documentary's verdict becomes a doorway. The ancients did not need to know quantum particles for the story to remain astonishing. The astonishing thing is that human beings, beginning with practical measurements and simple numerical relationships, eventually developed mathematical structures capable of reaching into an invisible world. The path was not straight. It was not secret. It was not owned by one culture. It was cumulative, uncertain, and full of wrong turns. That makes it more human, and perhaps more mysterious. There is one final historical lesson inside that doorway. Civilizations do not become smaller when their achievements are described accurately. They become more visible. The discovery, error, refinement, exchange, and invention is richer than the fantasy of perfect knowledge, appearing fully formed in the distant past. It shows people working with the tools to them, extending what generations had learned, and leaving problems for later minds. That unfinished quality connects the ancient world to the modern one more honestly than any claim of total foreknowledge. Every age hands the next generation a mixture of insight and mystery. The final section returns to the monastery and the laboratory one last time, not to join them into a single tradition, but to let them stand apart beneath the same unanswered question. Why does reality contain order? Why can the mind recognize it? And why, when the correct mathematics is found, does the universe seem willing to answer in the same language? The story ends in quiet, not with a hidden manuscript being opened, not with a physicist admitting that an ancient civilization knew everything first, not with a final equation linking meditation to particle collisions. Instead, it ends with two forms of attention. In one place, a person sits alone and watches the movement of the mind. In another, a scientist watches an instrument for a signal buried inside noise. The first looks inward, the second looks outward. Their methods are different, their standards are different, and their discoveries cannot simply be exchanged. Yet both begin by accepting that ordinary appearances may be incomplete. The contemplative notices that thought changes from moment to moment. The physicist discovers that matter at small scales does not behave like the solid objects of daily life. The mathematician discovers that a relationship can survive after the original object disappears. The historian discovers that a familiar story can change when dates and documents are examined carefully. In every case, attention removes a layer of assumption. This is the final meaning of quantum monasticism. It is not a historical claim. It is a metaphor for disciplined inquiry at the edge of intuition. The phrase describes the strange willingness of human beings to spend years with questions that cannot be answered quickly. A mathematician may follow a structure no one else can see yet. A physicist may trust an equation whose implications feel impossible. A contemplative may return to the same simple act of attention thousands of times. A historian may search through fragments because one uncertain date can change an entire narrative. There is a kind of monastic patience in all of this. Not because the activities are identical, because each requires surrendering the comfort of immediate certainty. The title that began as a claim of validation has therefore changed into a meditation on limits. The limits of language, the limits of historical evidence, the limits of intuition, the limits of analogy, and perhaps the limits of the human mind itself. Yet limits are not the end of knowledge. They are where knowledge becomes more precise. To know that zero is not the same as philosophical emptiness is progress. To know that observation in quantum theory does not automatically mean human consciousness is progress. To know that entanglement does not prove every form of cosmic connection is progress. To know that a mathematical shortcut is not quantum field theory is progress. Each boundary removes an easy answer, and each easy answer, once removed, reveals a deeper question. What is a quantum state telling us about reality? Why do symmetries organize physical law? Why are mathematical structures so effective? How does consciousness arise? How much ancient knowledge has genuinely been lost? How often do different cultures discover similar ideas independently? None of these mysteries needs exaggeration. They are large enough already. For the listener drifting towards sleep, perhaps this is the final comfort of the story. The unknown does not have to be filled immediately. A question can remain open without becoming empty. The dark can contain structure, even when the eye cannot see it. This may be the lesson shared, in the broadest possible sense, by the monastery and the laboratory. Pay attention long enough, and the obvious becomes uncertain. Remain patient long enough, and the uncertainty becomes structured. Test the structure carefully enough, and some part of it may become knowledge. The process is slower than revelation. It is also more reliable. Perhaps this is why the greatest discoveries often look simple only after they have been made. A short equation can hide years of failed ideas. A compact proof can hide generations of mathematical development. A clear historical conclusion can hide archives of contradictory evidence. A single experimental result can hide decades of engineering. The final form is compressed. The path that produced it is not. That may be the last connection to the sutra ideal. Human beings admire short rules because they seem to hold more than their size should allow. But a short rule is meaningful only because of the structure behind it. Without that structure, it is only a phrase. The same is true of the title of this documentary. Quantum monasticism sounds like a secret waiting to be decoded. By the end, the secret is different from the one promised. Modern particle physics has not revealed that ancient Vedic mathematics contained a forgotten quantum theory. It has revealed something more universal. Human beings can create abstractions, test them, refine them, and sometimes discover that nature responds with consistency. The ancients participated in the long history of that capacity. Modern physicists push it into realms the ancients could not have imagined. Future thinkers may look back on modern physics as another early stage. They may possess concepts that make today's deepest puzzles appear as simple as old arithmetic. If so, the pattern will continue. Complexity will become structure. Structure will become language. Language will open another mystery, and the human mind will follow. Perhaps that is why bedtime is the right place for this story to end. The demand to resolve questions can soften. The mind can hold uncertainty without turning it into fear or belief. Ancient formulas, modern detectors, philosophical emptiness, quantum fields, and distant histories can remain separate while still belonging to one effort to understand. The listener can notice the recurring gesture. Look again, define more carefully, test what can be tested, and leave the rest open until better evidence arrives. Somewhere beneath a detector, a signal will appear. Somewhere in a quiet room, a symbol will be written. Someone will notice that the pattern repeats. Someone else will ask why. And for a moment, the universe will seem to lean closer. Not because it has confirmed an ancient secret, but because a mind within the universe has recognized something true about the universe itself. That is the final mystery. Not whether the ancients already knew quantum physics, but why reality possesses patterns that can be known at all.